This video presents Hugh McGuire's algorithm for iterating over all possible community assignments. For you real mathematicians listening, when I say community assignment, I really mean K-cover. But for this video, I'm going to use the term community assignment to be consistent with the rest of our social networking research here at Grand Valley. This video contains a fair amount of motivation and background. In particular, we'll spend a couple of minutes explaining the limitations of the obvious, straightforward algorithm. Feel free to skip directly to those sections of the video that interest you. In our introduction to community finding, we explained how a social network like Facebook can be described as a graph where the vertices are people and the edges represent some relationship between them, such as friendship. If you look at such a graph, you can often see communities, groups of nodes that appear to be more tightly connected to each other than the rest of the network. Community finding is the process of identifying these communities based on the link structure of the graph. For a given social network, there are many possible community assignments, some of which are reasonable, but many of which aren't, in that they don't appear to describe how the nodes of the network interact. Notice it's not clear at a glance which of the top 3 assignments best describes the network's community structure. As explained in the introductory video, we need an objective function to quantify the quality of a community assignment. The simplest community finding algorithm is to simply generate all possible community assignments, apply the objective function to each one, and choose the best one. However, this simple approach isn't practical in general, because there are simply too many possible community assignments to evaluate. For example, generating all the possible ways to assign 34 people to 3 groups would take trillions of years on an Intel i7. As a result, current community finding algorithms are heuristics. That means they make educated guesses as to where to look for good community assignments. These algorithms may not necessarily find the best community assignment, but they usually come reasonably close in a reasonable amount of time. In spite of the exponential growth in running time, we believe that this brute force algorithm can be useful in very specific situations. Think of a community finding algorithm as a search through a very large, very complex landscape. So big and complex that we can't examine every square inch. Community finding heuristics make educated guesses about what areas to examine closely and what areas to skip. This is why they don't always find the best answer. Sometimes they skip the area containing the best answer. For example, if a heuristic searching this landscape for a minimum value decided to skip the tall blue mountain, it would miss the deep caldera containing the minimum. Running a brute force algorithm on a small graph is analogous to generating a detailed inch-by-inch map of a small landscape. We expect that examining the details of a small landscape will provide insight that we can use to improve our community finding heuristics as they search through much larger landscapes. For example, we may learn how likely our search space is to have features analogous to the calderas in these landscapes. If we know about such features, then we can be sure to tune our heuristics to look for them. Also, we currently don't know just how close to optimal existing heuristics get, because we have no way to compute the optimal. If we could compute the optimal, we probably wouldn't be using heuristics. Using brute force may give us a better idea of whether our heuristics generate answers that are nearly optimal like we see here, or if there's a lot of room for improvement. The extent to which results on a small graph will extrapolate to a larger graph is yet to be seen. This video presents an algorithm by Hugh McGuire for iterating over all possible community assignments. The algorithm is fast. It can generate 64 million assignments per second on an Intel i7, but it must generate the community assignments in order. For example, in order to generate the 100th community assignment, one must first generate the 99 previous assignments. In contrast, Professor Kermis's unranking algorithm can directly generate an assignment from an index alone. For example, it can generate the 100th community assignment without having to generate the previous 99. But it's considerably slower. Of course, that could change as we work on both algorithms, but for right now, McGuire's algorithm is about 16 times faster. We'll present this unranking algorithm in a separate video. Before I move on to explaining McGuire's iteration algorithm, I want to make one point perfectly clear. We're using brute force only as a tool to help develop and evaluate community finding heuristics. We are not in any way claiming that brute force is or can become a viable general-purpose community-finding algorithm. Also, we're not claiming that parallelism will make a brute force approach viable. It doesn't matter how many cells your GPU has, the number of community assignments simply grows too quickly to attack the problem in general by brute force. Unless, of course, somebody discovers that P is in fact equal to NP. McGuire's iterator algorithm is modeled after the iterators you would use with the Java or C++ collection library. The basic idea is that we define a total ordering for the community assignments, which means we line them up and give them each a specific place in line. And then we implement a next function that, when called, returns the next community assignment in line. The iterator object maintains some state describing the current position in line. For a Java array list, the iterator object maintains the index of the next item in the array to be returned. Our algorithm's iterator is a little more complicated, but more or less maintains some state describing the last community assignment returned and the changes that need to be made to generate the next one. We define a total ordering for community assignments by simply representing each assignment as a bit string, and ordering them by representing the bit string as a binary number. Also, to keep these bit strings the same length, each iterator object is configured for a specific value of n and k. For example, one iterator object may generate all the assignments of 8 people to 3 groups, a different object can generate all the assignments of 8 people to 4 groups, and so on. If you want all the ways to assign n people into communities, then you need to just simply create one iterator for each value of k, each possible number of communities that you want. So now let's look at the details of the algorithm. Naively, there are 2 to the nk ways to assign n nodes to k communities. We can see this by representing each node as a string n bits long. Each bit tells us whether that particular node is a member of that community. In this example, we can see that community 0 contains nodes 1, 3, and 4. Community 1 contains nodes 0 and 2, and community 2 contains nodes 2 and 1. The assignment defines k communities, each represented by n bits, for a total length of n times k. This allows for 2 to the nk unique values. This encoding leads to a very simple but incomplete algorithm. For each possible value in the bit string, so each value of I from 0 to 2 to the nk minus 1, we can interpret I as a community assignment. Take that bit string and generate the community assignment represented by it. And then we can evaluate the objective function for that community assignment and remember which one has the smallest value. This naive algorithm almost works, but it has a few problems. First, some bit strings don't represent a valid cover. For example, here, community 2 is empty. No nodes are assigned to it. Similarly, some bit strings fail to assign nodes to any community at all. In this case, node 3 is not assigned to any communities. Also, the naive algorithm produces redundant community assignments. Notice that all 6 bit strings here represent the same community assignment with a different labeling of the communities. For example, sometimes the community containing nodes 1 and 2 is labeled 0, sometimes it's labeled 1, and sometimes it's labeled 2. This isn't technically a bug, but it does mean we evaluate k factorial times as many assignments as necessary. We could fix these problems by looking at all 2 to the nk possibilities and simply ignoring the ones that we don't want. But we'd like to be more efficient. To see how we avoided generating undesired assignments, think of the bit string as an odometer in base n with k dials. Each column shown here is a dial that contains the numbers 0 through 2 to the n minus 1 written in binary. The binary number specifies the membership of each community, as we saw earlier. The next function simply advances the rightmost dial by 1. When the rightmost dial reaches all 1s, it then rolls around back to 0, and the next dial over advances by 1. Using this model, it's very easy to avoid empty communities. We simply remove 0 from each dial. Since 0 doesn't appear on any dial, we never specify any empty communities. Avoiding unassigned nodes is a little more difficult. We detect unassigned nodes by taking the OR of all the communities. Any zeros in the result represent unassigned nodes. At first glance, it appears that we can address this problem very simply by assigning any previously unassigned node to community 0. However, this quick fix causes a problem. When we add node 3 to community 0, we skipped 7 community assignments. 5 of these assignments, the ones in red, are invalid, but another 2 are valid, and we certainly don't want to skip them. In my opinion, the most clever part of McGuire's algorithm is his technique for skipping directly to the next valid cover. To see how this works, let's begin by looking at communities 1 and 2. Or, in the general case, looking at all the communities except community 0. We can see that, taken together, these communities have assigned nodes 0, 2, and 4, which means that nodes 1 and 3 have not yet been assigned. At this point, the algorithm will only modify community 0, which means that community 0 must contain these unassigned nodes. The current proposal for community 0 assigns nodes 1, 2, and 4, which means that in this assignment, node 3 is missing, thereby rendering the entire proposed assignment invalid. As we just saw, simply adding node 3 to community 0 will produce a valid community assignment, but not the one we're looking for. So what exactly are we looking for? Well, because we're generating community assignments in numerical order, the numerical order of the bit strings, we want to find the smallest value for community 0 that's larger than the proposed value and also contains nodes 1 and 3. That is, the nodes that haven't been assigned yet. So how do we find this value? Well, we'll begin with the proposed value. This is a lower bound on the number we're looking for because if you assume that we've already set our values for community 1 and 2, we've already considered all the community assignments with lower values for community 0. We know we need to generate a different number. To get a different number, we need to change some of the bits in this proposed value. Changing any of the 1s to 0s will make the number smaller and take us below our lower bound. So instead, we'll change some of the 0s to 1. In particular, we'll change the bit for the most significant missing community from a 0 to a 1. As we've seen, this can potentially skip over some of the valid assignments. But changing this value allows us to change some of the 1s to 0s. In particular, we can change all of the bits to the right from 1 to 0 without going below our lower bound. We now have the smallest value for community 0 that has bit 3 set and is above the lower bound. Setting the remaining bits not yet assigned produces the desired result. The smallest value greater than 10110 that also has bits 1 and 3 set. Finally, we address the redundant assignments. As we saw earlier, these 6 bit strings are all identical. They represent the same community assignment with the communities relabeled. We want a rule telling us which of these 6 to generate so we don't waste time touching the other 5. McGuire's algorithm does this by generating only the assignments where the bit strings increase in value from left to right. The challenge is to generate only these increasing representations. To do this, we initialize the counters to 1 more than the counter to the left, thus maintaining the desired increasing property. When we do this, we must also limit the maximum value of each counter. For example, the counter for community 1 must stop at 11110, because if we set it to 11111, there wouldn't be any legal values left for counter 0. The C implementation of our algorithm can generate about 64 million community assignments per second on the Intel i7s we have in our lab. That means in 1 hour we can generate all of the assignments of 7 people to 7 communities. If we allow the algorithm to run for 24 hours, we can generate all of the assignments of 6 people to 12 communities. When you compare what you can do in an hour to what you can do in a day, you can see just how rapidly the problem grows. This algorithm has one main limitation. All assignments must be generated in order. There's no obvious way to start in the middle. This means that there isn't a good way to use the algorithm to generate a random sample of assignments, nor is there a good way to parallelize the algorithm by dividing it into many equal pieces. We can approximate an equal division by evenly dividing all 2 to the nk possible bit strings. For example, we can divide the algorithm into 4 pieces by finding the first assignment that begins with 0, 0, the first assignment beginning with 0, 1, the first assignment beginning with 1, 0, and so on. However, because the values on each dial increase left to right, there will be many more valid bit strings that begin with 0, 0 than with 1, 1. If we could easily count the number of assignments in each group, we could generate a large number of groups and then use a bin packing heuristic to balance them over a smaller number of processors or cores. This, of course, is an opportunity for future work. Kermis's unrank algorithm avoids this limitation, but the current implementation is much slower. This unrank algorithm is the subject of our next video. Thanks for watching.